This is the lecture for the 21st chapter in our textbook. We will cover the principles needed to understand heat engines and refrigerators. Let's get started. As we have stated previously, thermodynamics is the branch of physics that studies the transformation of energy. You are probably aware of many devices that transform energy as heat into work. We have spent the past few weeks motivating the first and second law of thermodynamics, that delta E internal equals Q plus W, and that heat energy is transferred spontaneously from a warmer system to a cooler system, and never from a cooler system to a warmer system. Recall that the work W in our first law is the work done on the system by forces due to the environment. We will say that the work done by the system is W sub S, which is the negative of the work done on the system. This is also the area under the PV curve. We could rewrite our first law as Q equals W sub S plus delta E internal. We now introduce the ideal thermal reservoir. An energy reservoir is capable of transferring energy in or out without undergoing a temperature change. A high temperature reservoir is one at a higher temperature than the system. A low temperature reservoir is one at a lower temperature than the system. Here we see examples of energy transfer diagrams. In the diagram to the left, energy is transferred from the high temperature reservoir to the low temperature reservoir by passing through a copper bar. By conservation of energy, the energy that is transferred from the high temperature reservoir must equal the energy that is transferred to the low temperature reservoir. The diagram shows the direction of the energy transfer. The diagram to the right does not represent a physical situation for a spontaneous transfer of heat, as heat is not spontaneously transferred from a low temperature reservoir to a high temperature reservoir. We begin by discussing turning work into heat. We see an example of an energy transfer diagram for this process. A simple example of this is rubbing two objects against one another. The conversion of work into heat is 100% efficient over a long enough time horizon. The reverse process of turning heat into work is not as easy or as efficient. Some requirements for a device meant to transform heat into work include that it must reset to its original state and be ready for continued use. It is not possible to create an engine that transforms heat into work with 100% efficiency and resets to its initial state. This is established by the second law, as heat only flows from the higher temperature object to the lower temperature object. Which is an isochoric process in which heat is removed from the system. A, B, C, or D. Since no work is done in the isochoric process, and we want the case where heat is removed from the system, then the change in internal energy should be negative. Case D represents an isochore, where the temperature will decrease. In a steam turbine of a modern power plant, expanding steam does work by spinning the turbine. The steam is then condensed to liquid water and pumped back to the boiler to start the process again. First heat is transferred to the water in the boiler to create steam, and later heat is transferred out of the water to an external cold reservoir in the condenser. This steam generator is an example of a heat engine. Here we have the energy transfer diagram of a heat engine. All state variables, pressure, temperature, thermal energy, etc., return to their initial values once every cycle. The work done per cycle by a heat engine is W out equals Q net equals Q hot minus Q cold. The thermal efficiency of a heat engine, eta, can be defined as the work output W out divided by the heat extracted from the high temperature reservoir, Q hot. This is then also equal to 1 minus Q cold over Q hot. In practice, the thermal efficiency for car engines and steam generators ranges from about 0.1 to about 0.5. Let's try an example. Here, 100 joules is extracted as heat from the high temperature reservoir. The system then does 40 joules of work on the environment. Finally, 60 joules is expelled as heat into the low temperature reservoir. What is the efficiency of this heat engine? The work done by the system divided by the heat extracted is 0.4. Let's look at another example. First, heat is transferred into the gas from the burning fuel. We have isobaric heating and expansion of the gas. The gas then does work by lifting the mass m. We could then lock the piston in place, remove the mass, and turn the heat off. The gas will cool, but the piston is locked, so this is done at constant volume. If the piston is then unlocked, we can then increase the pressure on the gas while compressing it isothermally. In so doing, we can return the gas to its initial pressure and volume. Here we map these processes onto a PV diagram. From 1 to 2, mass is lifted in an isobaric expansion. From 2 to 3, no work is done, as the process is an isochoric cooling. From 3 back to 1, the piston is compressed until the gas is returned to its original state. The net work done each time a cycle is completed is W lift minus W external equals the work done by the system from 1 to 2 plus the work done by the system from 3 to 1. In a sense, a refrigerator or air conditioner is the opposite of a heat engine. In a heat engine, heat energy flows from a hot reservoir to a cold reservoir, and work out is produced. In a refrigerator, heat energy is somehow forced to flow from a cool reservoir to a hot reservoir, but it requires work in, to make this happen. Here we have an energy transfer diagram of a refrigerator on this slide. Here we see energy is drawn from the low temperature reservoir, work is done on the system, and then an amount of energy equivalent to the energy drawn from the low temperature reservoir plus the work done on the system is expelled into the high temperature reservoir. At the end of each cycle, all state variables are returned to their initial states. The purpose of a refrigerator is to remove heat from a cold reservoir, and it requires work input to do this. We define the coefficient of performance K of a refrigerator to be equal to the heat extracted from the low temperature reservoir divided by the work input into the system. Since heat does not flow from a cooler system to a warmer system of its own accord, there is no such thing as a perfect refrigerator in which K tends towards infinity. We examine a refrigerator in which 60 joules is extracted from a low temperature reservoir when 40 joules of work is done on the system and 100 joules of heat is expelled into the high temperature reservoir. What is the coefficient of performance for this refrigerator? Here we find that 60 joules divided by 40 joules is a coefficient of performance of 1.5. We can also see that this prevents us from having a perfect heat engine, as well as this would allow us to create a workaround for heat flow from cold to hot without any cost. Some heat engines use an ideal gas as the working substance. A gas heat engine can be represented by a closed cycle trajectory on a PV diagram. The net work done during a full cycle is W out equals the work done during expansion minus the absolute value of the work done in compression. This is the area inside the closed PV curve. We can put this to practice here. How much work is done in one pass of the given cycle? The enclosed triangular area is 2,000 joules. Here we see a pair of tables summarizing our findings from the past few weeks. These are tables 21.1 and 21.2 from your textbook. They are quite useful. Even in a refrigerator, heat is always transferred from a hotter object to a colder. The gas in a refrigerator can extract heat QC from the cold reservoir only if the gas temperature is lower than the cold reservoir temperature Tc. The gas in a refrigerator can exhaust heat QH to the hot reservoir only if the gas temperature is higher than the hot reservoir temperature TH. If a perfectly reversible heat engine is used to operate a perfectly reversible refrigerator, the two devices cancel each other out. A heat engine more efficient than a perfectly reversible engine could be used to violate the second law of thermodynamics. Thus we say that no heat engine can be more efficient than a perfectly reversible engine. The maximum possible efficiency of a heat engine, eta max, is that of a perfectly reversible engine. The maximum possible coefficient of performance of a refrigerator, Kmax, is that of a perfectly reversible refrigerator. A perfectly reversible engine must use only two types of processes. One, frictionless mechanical interactions with no heat transfer, Q equals 0. Two, thermal interactions in which heat is transferred in an isothermal process, delta E internal equals 0. Any heat engine that uses these two types of processes is called a Carnot engine. A Carnot engine is a perfectly reversible engine. It has the maximum possible thermal efficiency, eta max, and if operated as a refrigerator, the maximum possible coefficient of performance, K max. The Carnot cycle is an ideal gas cycle that consists of two adiabatic processes, Q equals 0, and two isothermal processes, delta E internal equals 0, as shown. These are the two types of processes allowed in a perfectly reversible gas engine. As a Carnot cycle operates, the gas is isothermally compressed at Tc. Heat energy Qc equals Q12 is removed. The gas is adiabatically compressed with Q equals 0 until the gas temperature reaches T hot. After reaching maximum compression, the gas expands isothermally at temperature T hot. Heat Q hot equals Q34 is transferred into the gas. The gas expands adiabatically with Q equals 0 until the temperature decreases back to T cold. Work is done in all four processes of the Carnot cycle, but heat is transferred only during the two isothermal processes. We can write the second law informally as no heat engine operating between energy reservoirs at temperatures T hot and T cold can exceed the Carnot efficiency equal to 1 minus T cold over T hot. We can also say that the coefficient of performance equals to T cold over the difference of T hot and T cold on an absolute scale. What is the efficiency of this Carnot heat engine? From formula or diagram, we see that this Carnot heat engine has an efficiency of 0.5. What is the efficiency of this heat engine? Since it is not a Carnot engine, it must be less efficient than a Carnot engine operating between the same two temperatures. Therefore, it must be less than 0.5. Okay, that is all for today. As always, you are all awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.